Lesson 5, this is the second activity. Give an accurate sketch of the derivative of the function shown below. So for this one, I'm just going to pick one arbitrary point here, for example, that guy, and ask what the tangent line looks like at that one spot. And hopefully we see that the tangent line at that one spot is the line itself. And since we're interested in knowing what the slope of that tangent line is, it seems like we should calculate the slope of each of the line segments that make up this graph. So the slope of this first one, just counting boxes, up 1 over 1. Slope of that one is 1. Slope of this next one, I think, is just -1. This next one here, be careful. This one's steeper. So count, change in y over change in x. I get the slope there is 2. I think it's also a slope of 2 on this next uphill one. And then finally, the downhill one, counting carefully, slope looks like -2 to me there. Okay, so I am going to, I'm just going to not very accurately graph those things. Well, I'm going to graph them accurately, but I'm not going to pay attention to the places where the rules change. I've got some corners and I've got some jumps here. So I'm just going to graph slopes of 1 from beginning of time until -3, right? I've got a slope of 1 from the beginning of time until -3. So that means that the derivative is constantly 1 from the beginning of time until we get to -3. And then I've got a slope of -1, and that happens from -3 out to, nope, too far, -3 out to 0. From here to here is where I have a slope of -1. From -3 to 0 is where I've got a slope of -1. So -1 like that. And then I've got a slope of 2. The slope of 2 starts, it goes there to there. So that's from 0 out to 2. So let's graph that. From 0 to 2, I've got a slope of 2. Constantly 2, always 2 between 0 and 2. And then the next one, so that's from here all the way up to the top there, which I'm guessing is at 5. That is also a slope of 2. So from 2 to 5, I continue to have a slope of 2. 2 to 5, I'm going to erase that for just a little bit. 2 to 5, I have a slope of 2. That goes to there. And then finally, I've got a slope of -2 from 5 until the end of time. So -2 starting at 5 and then going to the right forever. Okay, so the only question is what's happening at the places where this thing jumps around and what's happening at this gap right over here. All right, so at the first spot where things change, the rules change, is right here at x equals -3. Let's analyze. X equals -3 is a corner, and that means that the derivative doesn't exist. We know that the derivative doesn't exist at corners. Open circle there, open circle there. It wouldn't make any sense to fill in one of those open circles over the other, right? They're both equal. They're equivalent, I guess. And you certainly can't fill them both in because then that would say that the derivative is defined, right? It would be simultaneously 1 and -1, and that's no good. Okay, the next place we're going to look is the next place that the rules change. I'll actually look up here. I see I've got another corner at 0. This is x equals 0. And so at x equals 0, again, we're going to have open circles. X equals 0 and x equals 0. Okay, next thing where something wacky happens is right here at x equals 2. There is a big old jump discontinuity here. And so therefore the derivative doesn't exist at x equals 2, which is kind of surprising because it sure feels like I could ignore an open circle there and just draw a horizontal line, right, going straight on through just like that. But you can't do that. The derivative does not exist there, even if the derivative is 2 to the left of that point and +2 to the right of that point. It's no good because it's discontinuous. This function is discontinuous. The derivative does not exist. And the last thing is at x equals 5. There's a corner. So that means that the derivative doesn't exist at x equals 5. So we got 2 holes there. Next page, this one is not going to be as exact, as accurate as the previous one. It's a very rough sketch here of the derivative of the function shown below. Okay, let's give this a shot. I will start by picking this point over here. Should I start there? Maybe no. Let's follow my convention from before. I like starting with places where the original graph is flat, so I can see a horizontal tangent line right there. In fact, I can't see any other horizontal tangent lines. I guess maybe here, maybe. So this is the point -2, that's my x, and then the slope is 0. Remember, it's x comma slope. And then all of these points in here are something, comma, and then if it truly is flat, they're all 0. So let's see if we can graph now. So -2, 0, that's right there. And then I've got a whole interval of points, maybe from -6 all the way over to -4, -6, -6 to 4. Got this whole family of 0 horizontal tangent lines, 0 slopes. Okay, so let's pick a point over here, maybe this guy, and very roughly eyeball that. I'll call it a -2. Don't even need you to count boxes here. And so the estimate for my x-coordinate at that red dot is maybe 7.3, and then the slope is -2. So -7.3, -2, which would be right there. Okay, so I feel good about, like, I've captured this part, and I've captured this part. So now I need a point in here and maybe another one over there. So let's do that. So we'll go purple one right there and another purple one right over here. So the slope here, again, very rough. Maybe the slope there is -1. This looks, maybe it's a symmetric +1. And so that means that we estimate the x. So how about -3.5? And then the slope, -1. And then over here, we estimate the x, -0.5, comma, slope 1. So -3.5, -1, -0.5, 1. Something like that. Okay, and then we continue on until something happens at x equals 1. Now I see a corner there. In fact, I saw a corner over here. So we'll deal with those corners at the end, but I can't do anything at x equals 1. So we're not going to pick that point, but we could pick a point just a little bit to the right of that. So maybe we could pick this one here, and then something's happening here, and then we'll pick maybe this one up here. So this first one, draw a tangent line. Maybe that one is also a +1. So if I'm estimating the x-coordinate, maybe 0.6, comma 1. I'm going to skip the one in the middle. I'm going to go to this last one here and say that this one is probably about the same, x equal m equals 1. Maybe it's not quite as steep there. Doesn't really matter which one you pick. I'll say m equals 1 there. And if I can estimate the x-coordinates of this point, maybe 2.4. And then the slope is 1. So let's plot these points that we just came up with, the two orange ones, 0.61 and 2.41. 0.6, comma 1, 2.4, comma 1. Okay, but something is happening at that one spot in the middle there. This yellow highlighted spot is a point of vertical tangency. And so the derivative doesn't exist there, but it sure leads me to believe that as we walk along this curve, the tangent lines are getting steeper, steeper, steeper until they're vertical for just one moment in time, and then shallower, 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 but really steep in the beginning. All right, so we'll come to that at the end. Let's just finish up the right-hand piece of this graph. Okay, so this last one, we can pick any point that we want here. In fact, this last segment right here is linear, which means that we just need the slope of that line itself. So any point over here has whatever slope it has. I don't see any nice points that I can grab, so I'll just estimate the coordinates of the beginning and the end. So we'll say that this is 7, comma, -0.8. And we'll say this one up here is 4, comma, 2.2. And so then calculating slope of that, 2.2 minus -0.8 divided by 4 minus 7. So that's a 3 over -3, -1. So the slope is -1 everywhere between 4 and 7 on that whole line. So from 4 to 7, it's a -1. 4 to 7, it's a -1, just like that. Okay, so let's see if we can put things together now to connect these disparate pieces that we have. Okay, so the beginning part, this one where I had this red tangent line, really steep, negative, still pretty steep negative, but flattening out, getting towards 0. So we're drawing something which is really negative and then not quite so negative, and then eventually getting to 0. The question is, what about at the transition? So looking at this spot right here, is that a corner? And I think you could argue that it is not. It sure looks like a smooth transition from one to the other. So we don't need to just put like, you know, like an empty hole here or anything like that. Okay, so we've got that part, and now we've got the next piece is already in green. So this piece right here is taken care of. And then here we had some negative stuff and then 0 and then some positive stuff. So let's see if we can do that. So it goes, I got some negative stuff and then 0 and then positive stuff. Okay, so negative stuff, 0, and then positive stuff, something like that. But there's still this gap, like what's happening right in here, right? Like, am I supposed to connect that? And the answer is no. If you take a look at this point right here, that is a corner, and the derivative does not exist there. And the derivative very rapidly changes from being 0 to being, you know, like -1 and change. And so we are just going to extend this a little bit out. I'll put an open circle there, open circle there. It is a big old jump from a derivative of 0 to a derivative of -1.2 or something like that. Okay, moving on. I think we're up to here-ish, and so the derivative gets bigger, bigger, bigger until we get to that corner. Okay, so I guess that means I need to estimate like the last derivative up here on this parabola-looking piece. So if I called this one a 1, then I guess I got to say that the last derivative here is maybe something steeper, like a 1.5 or 2. And so that happens at x equals 1. So at x equals 1, we're going to just keep on trucking until we get out to about 1.5, something like that. Did I go too far? I messed up my my point before. I see now right here where I said 0.6, I should have said 1.6. I'm sure you knew that long ago. We'll fix it right there. And then we'll fix this guy right here. It was supposed to be at 1.6. There we go. Okay, so what we were doing before was extending this thing until we get out to 1, and that's where the rules change. And then if I'm looking at this next piece right in here, it looks like it's a positive slope, but not quite as big. So positive slope, not quite as big. So maybe something like this. So I don't know exactly what number it is down there. Positive, not too big, not too small. And then we got to take care of that vertical asymptote. We said at x equals 2, that tangent line, it's highlighted in yellow, is vertical. And so that means that the tangent lines get steeper, 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 never actually quite touch there. And then just on the other side, super steep, but then coming down. So that's the idea there, vertical tangent line. Okay, and then I guess one last thing we need, and then we're done. This is another corner, so we know the derivative changes rapidly at that spot. So I'm just thinking about like the last tangent line, quote unquote, last tangent line. I'll call that a slope of 0.3, I don't know. And then we've already got that one calculated. So let's say that it goes to 0.3 when x is 4. 0.3 when x is 4, maybe something like that. So it just comes down here and then abruptly stops and changes its mind. Need an open circle down there as well. And that's it. Phew, these are tough. Okay, next page. Sketch the graph of a function that meets all of the following criteria. Erasers were designed for problems like this. Let's give it a shot. We need something that's continuous everywhere except at x equals 2. I don't know what to do with that just yet. Not differentiable at those 3 x values. Don't know what to do with that either. Graph of x has a vertical tangent line at x equals -2, but nowhere else. All right, that I can do something with. At x equals -2, we need a vertical tangent line. So I'll just put like a sorry, that is not what I meant to do. So we're graphing f here. Okay, so we need a vertical tangent line at x equals -2, but nowhere else. So maybe something like this, vertical at x equals 2, and then coming out. And it needs to be not differentiable at -2. Okay, that's already taken care of because it's a vertical tangent line. But I also want it to be not differentiable at x equals 4 and at x equals 2. So at x equals 2, it says continuous everywhere except at x equals 2. Okay, super. So then I can just continue this graph over here until I get to x equals 2. Then I'm allowed to make something that is not continuous. And as soon as I have that jump discontinuity, this function here is not continuous at x equals 2 and therefore also not differentiable at x equals 2. Okay, and then finally, x equals 4. Need to make it not differentiable, but it can't have a vertical tangent line and it can't be discontinuous. So this forces us to use the third kind of common way for a function to be not differentiable, and that's to have a corner. And so I've already failed because right here at x equals 4, it is smooth. I need it to not be smooth. I need it to have a corner. Something like that. And then we'll extend all the way to the edges of the graph paper. This is one acceptable answer. There are infinitely many acceptable answers, but hopefully you got the gist of it here. One vertical tangent line, one discontinuity, and one corner.